Okay, great. Thank you. Thanks to the organizers. I'm happy to be here. Let's see. Yeah, so I'll talk about Gromov-Wasserstein distances and applications to shape graphs. This is joint work with Martin Bauer, Facundo Mémoli, Nishino, and then kind of separately, Aditi Basu Bal, Xiaoying Guo, and Anu Shrivastava. So mostly the talk is about Gromov-Wasserstein distances, which is this first paper, and then this kind of ties into the shape analysis theme through the second paper, which chronologically came first, but in retrospect is related to what we did, which I'll explain as we go through the talk. Okay, so as motivation from shape analysis, the goal is to extend shape analysis methods. By this, I mean like computing geodesics between shapes, doing geometric statistics by pulling things back to tangent spaces, etc., computing for means, all of that stuff, to the setting of shaped graphs. By that, I mean basically like graphs, embedded graphs whose edges have shapes associated to them. So these kind of one-dimensional stratified spaces sitting inside RD, examples being like arterial networks, okay, or like road networks, or many other such examples. Okay, so I would like to be able to take, for example, a collection of road networks and compute a mean of those, and then compute like PCA of that collection, for example. So let's see. So the model that we'll use is based on optimal transport. And we'll develop this tool which allows us to compare shape graphs, but in fact is really much more general, okay, and will allow us to compare all sorts of structured networks. Okay, so let's dive into that. So yeah, like I said, it's based on optimal transport. I won't dwell too much on the definition here because I think most of this crowd knows this story, but just to make sure we're all on the same page with notation. So I want to talk about Wasserstein distance, which is a way to measure distance between probability measures. So we start with the ground metric space, x dx, and then we have probability distributions, mu and nu on x, and we have a p parameter between 1 and infinity. This is like an LP sort of parameter. And then we can define the p Wasserstein distance between these distributions as this quantity. Okay, so this is sort of a compact version of the definition. Let's unpack this a little bit. So I'm taking inf over the space of couplings. Okay, so given mu and nu, I can think about couplings, which are joint measures on the product space. Here, look at this Wikipedia picture here. So I have like x cross x, so then I get this product space. I get a joint measure on the square, such that if I push to the left or push up, I recover my original measures. All right, so given a coupling, I compute kind of the quality of that coupling by this measurement, which says how much do I have to move points with respect to that coupling. Okay, so take this LP norm of distance. All right, so that's Wasserstein distance. I want to extend that to the setting where my measures can live on different metric spaces. And so going back to the motivation, basically it's like if I want to compare two graphs, I want to think of these as kind of individual structures, so each of these is like its own metric space. I don't have a ground truth correspondence between the nodes. Okay, so in order to do this, I need to extend the theory of optimal transport to handle this situation where I have two different metric spaces. All right, so let's see. So I let x and y be metric measure spaces. So by that I mean metric spaces, or x dx is a metric space, and then I'm picking a probability measure on x, call it mu x. Same for y. I'm suppressing kind of like technical assumptions here, so you probably want to assume that these are Polish spaces, things like that. So that's kind of all under the hood here. But then I can compare two such objects by this thing called Gromov-Wasserstein distance. This also depends on a parameter p. So this is due to Facundo Mémoli in 2007. And yeah, so the structure is, I would say, similar to Wasserstein distance. Okay, so I'm still infamizing over couplings. Coupling still makes sense even if the measures live on different spaces. It's still a product or a joint measure with prescribed marginals. Okay, given one of those, the difference here is how do I measure the quality of a coupling? Okay, Yes, this was a copy-paste error, thank you. So this should be mu x and mu y, thank you. Yeah, so I'm coupling mu x and mu y, and then the point is I change how I measure the quality of a coupling, okay? Now I don't have a notion of distance between points in x and points in y, I can only do this kind of relatively, okay? So I can measure the distance between a pair of points in x and a pair of points in y, and I can say how do those compare to each other, right? So the thing I'm taking the LP norm of is the function dx minus dy, which I think of as a function from x cross y to r, okay? Let's see, so this is, yeah, this formulation here is for p less than infinity. The 1/2 is a normalizing factor, which makes it so that when p is infinity, this basically looks like Gromov-Hausdorff distance. Okay, it's not exactly the same, but it's very close to being Gromov-Hausdorff distance for p equals infinity. Maybe let's try to get some intuition for what's going on here if you're not familiar. So what are we doing? The way I think of this intuitively is if I pick a coupling of mu x and mu y, this is telling me how to register the points between the two spaces. Okay, so I don't know a correspondence between x and y. I'm choosing one, and it's kind of like a soft correspondence, so I'm allowed to take mass from a point x and kind of like subdivide it amongst points in y, okay? So I can spread mass out from points in x to different points in y, so it's like a soft registration, is the idea. Okay, so if I pick a soft registration, this is telling me how to send mass from points in x to points in y, and then the quality of that registration is how much does that registration distort the respective metrics, okay, overall. Cool. All right, so yeah, so you can define this thing, and then it's theoretically well behaved in some respects at least. So in Facundo's original paper, he proves that the PGW distance, the P-Gromov-Wasserstein distance, defines a metric on the space of compact, fully supported metric measure spaces up to measure-preserving isometry. What does that mean? It means it defines really a pseudometric, but you get distance 0 when the things are related in this precise way. So if there's a function from x to y, which takes mu x to mu y, and which is an isometry, so it preserves the metric, then I get a distance 0. All right, and observation, because people always ask this when I'm talking about this. So one thing you could do is say, well, what if the underlying metric spaces were the same? And I'm just picking different measures on the same metric space. Then it would make sense to compute Wasserstein distance in that space, okay? And the Gromov-Wasserstein distance is a lower bound on that and not equal in general, okay? A simple example is take a distribution in Rn and rotate it. Okay, that's a positive distance move in Wasserstein distance, but that's a measure preserving isometry, so it's a distance 0 move in Gromov-Wasserstein distance. So yeah, so Gromov-Wasserstein doesn't distinguish between kind of like rigid motions of a measure. Right. All right, so that's Gromov-Wasserstein distance. Several variants of Gromov-Wasserstein distance have been introduced over the last several years. Let's start with this one, which is a very mild extension, I would say. So in this paper of Chowdhury and Mémoli, they consider triples, which are just slightly relaxed versions of metric measure spaces. So here I have still a measure space, x mu x, okay? The difference here is that I'm going to not require that this function in the middle here is a metric, okay? So I'm just thinking of this as some arbitrary kernel. So it's just a function which eats a pair of points in x and returns a real number. The motivation here is to say, well, okay, so if I'm doing some data analysis task on an ensemble of graphs, say, then I might not want to use like a distance metric to represent the graph. Okay, if I have a disconnected graph, for example, then like geodesic distance doesn't make sense. On the other hand, I could have like an adjacency matrix, and that still makes sense. Okay, and it comes with other benefits, like if it's a binary adjacency matrix, I can use I can speed up my matrix manipulation computation. Or I could use other types of kernels like Laplacians or heat kernels, for example. Okay. So I want to extend the purview of Gromov-Wasserstein distance to spaces with these kind of arbitrary kernels. And then I observe that if I take the definition of Gromov-Wasserstein distance and I just use those kernels in place of the metrics, that's a quantity that still makes sense, okay? And it still has reasonable properties. So this still defines as a pseudometric. A pseudometric meaning it has triangle inequality, it's symmetric, but it can take distinct things and give them distance 0. But the distance 0 equivalence relation in this setting is also understandable. So it's like a bigger equivalence relation than in the metric space setting. Okay, it's not just like measure preserving isometries, but it's still something that looks reasonable. Maybe come back to that. Okay, so that was kind of the first variant of Gromov-Wasserstein distance, and this has seen a lot of applications in machine learning. So like I referred to earlier, think of the situation where you have an ensemble of graphs and you want to do some sort of machine learning task. There's no correspondence between the nodes of the two graphs necessarily, so I don't know how to compare them initially. The Gromov-Wasserstein setting with this relaxation allows you to compare these two graphs. Part of its computation, I mean, the whole computation really amounts to finding a soft registration of the nodes, which is useful in its own right, okay? So this is just a bunch of random pictures from various papers, but it's seen a lot of uses in machine learning, basically. All right, so then further extensions of the framework have been introduced to deal with graphs that have attributes. Okay, so in practice, when you're dealing with a graph data set, you're not usually just handed kind of the raw graph structure. The graphs come with attributes on the nodes or attributes on the edges. Let's look at a concrete example. So if my data set is a bunch of molecules, or graphs representing molecules, then each node also has an atom type attached to it, and the edges have bond types attached to them, okay? So I have, and then if I have a metric on the space of atom types and a metric on the space of bond types, then I get attributes on the nodes and edges that live in different metric spaces, okay? So I won't give you the detailed formulation, but you can extend Gromov-Wasserstein distance to handle that situation. Basically, the idea is like there's a Gromov-Wasserstein component, which is able to compare the graph structure, and then there's kind of a Wasserstein component which compares attributes, because the attributes typically live in a common metric space. Great, okay, so we have these extensions, and many others, okay, I'll show you a big table with a bunch of obscure names of different Gromov-Wasserstein extensions in a second, but there have been like a dozen or so kind of extensions of this framework. And then now getting to the point of the talk, we introduce a general framework which kind of includes all of these at once, as kind of a single mathematical structure. All right, so yeah, so here's the definitions. So the idea is to define Gromov-Wasserstein relative to a kind of fixed target for your kernel. Okay, so I'm going to fix a separable metric space, Z. And then I define a Z network to be a triple that looks like kind of the kind of thing we had before. Okay, so it's X, omega, mu. X, mu is still a Polish probability space, just like before. The difference here is that my kernel doesn't take values in R, but takes values in Z. Okay, so omega eats a pair of points from X and returns some point in this fixed metric space, Z. And then I can extend the definition of Gromov-Wasserstein distance to handle those sort of structures. Okay, so everything is with respect to this fixed metric space, fixed metric space Z. Now, given two Z networks, so basically kernels valued in Z, I can compare them by extending Gromov-Wasserstein distance in this way. Let's pull up the classical definition here. All of the coupling should be between mu X and mu Y. Like before, yeah. Well, it depends what we might capture, I guess. It would be able to compare protein structures if you're thinking of these as attributed graphs. Yeah. I mean, so sure. At a node, you can assign an angle as an attribute. You can assign like local geometry as an attribute for sure. It's very flexible and kind of like any application you have in mind where you have attributes on a network. Any application at all, you can kind of fit into this framework. Right. So comparing to the old definition of Gromov-Wasserstein, or the classical definition, I should say, what's the difference? It's really a small difference. Okay. Previously, I had real valued kernels, and I compared the kernel values by taking the absolute value of their difference. Okay. I replaced that by taking their distance in Z. That's really the only distinction. So I would call this a fairly natural generalization. And then, of course, if your metric space is R with the obvious distance, then you recover classical Gromov-Wasserstein distance. Okay, so, but of course, for other choices of Z, you get other variants of Gromov-Wasserstein distance. So here's that table I was telling you. So the intention is not that you read all these and think that they make sense. This is like a kind of a wow slide. Look at all the things we're generalized here. But the point is, if you choose Z appropriately, you recover most of the variants that have been studied in the literature. And so the point here, to sum this up, is like in most of these papers, they prove the basic metric properties of their variants, fresh, right? They prove triangle inequality in each of these papers. The point is, we'll show that in general, this satisfies triangle inequality and various other properties. So the properties that each of these variants have follow from the kind of general picture of how this framework works. Okay, so so here's some summary table, but let's look at a couple of these in detail. Okay, so first we can think about Wasserstein distance again. Okay, so let's suppose that I have my target metric space Z, and I have two probability distributions on Z, mu and nu. I can think of those as defining Z networks by taking the underlying set to be Z in both cases. It's going to be the same kernel in both cases, which is just projection onto the first coordinate, so a very simple kernel, okay? And then the measures are different. If I compute the Z-Gromov-Wasserstein distance between those networks, right? So the point is the kernels just project on the first coordinate. Then I can integrate out one of these copies of pi, and I end up with Wasserstein distance up to a factor of, maybe this should be like 1/2 to the p, up to some constant factor. We recover Wasserstein distance. Okay, which is unlike classical Gromov-Wasserstein distance, which is not a generalization of Wasserstein distance. This is. Yes? Yeah. So in order for Wasserstein to make sense, that's the case. So then the point is, if you have two measures on the same space, you can construct these Z networks, which will recover the Wasserstein distance. Well, I mean, if you have some cost function or something, I suppose, but there's not like, I would say, a natural cost function coming from the intrinsic structure. That's kind of the point of Gromov-Wasserstein. This gives you a natural cost function. You have to pay the price if it becomes like this quadratic cost instead of a linear cost. Okay, and like I mentioned before, you have these situations where you have node or edge attributed graphs, like the molecules, or if you have like a social network or something, then maybe you want to encode the types of interactions that your users have or something that's like an edge attribute. Blah, blah, blah. Like it's easy to cook up examples where you have attributed graphs. And then, like I said, there have been versions of GW that have been introduced to handle those structures, and those are also examples of these Z-Gromov-Wasserstein distances, provided you choose your Z appropriately. In this case, it's something like an LP product of the network kernel and the metrics in the attribute spaces. All right, and then, so our motivating example was shape graphs, so that we can talk about shape analysis. Okay, so here's a way to think about shape graphs in this context. Yeah, so here's a shape graph. How do I want to think of this? I think of it as like a bunch of embedded curves in Rn. So I have some union of them, and they intersect at endpoints, right? So it's a bunch of open curves that are allowed to intersect at endpoints, and I get this one-dimensional stratified space. I can think of this object as a Z network, where Z is going to be some shape space. So I'm giving you some specific one here. There are other choices you might make. But I want to think of the underlying set X in this network as the intersection points of the curves. Okay, so these are like the vertices of the graph. Now, given two vertices, I assign an element of, say, like smooth maps into Rn mod diffeomorphisms, or maybe this should be immersions, or however you want to formulate this will work. Right, so then the point here is I have vertex, vertex, and the element that I'm assigning is that curve. My Z is like shape space. All right, so then that puts you in the setting of Z-Gromov-Wasserstein distance, where Z is this space endowed with some metric, and you know, maybe you pick a Riemannian metric on the total space, which is invariant to diffeomorphisms, and do some metric that way, or kind of however you want to do it. Whatever metric you like, you can use. Okay, so there are technical points, which I'm not going to write a lot about on the slides, but I'll sort of hand wave my way through how to handle them. Right, you might observe that the kernel function is supposed to take any two vertices and give you a curve. Okay, that's an issue. Like if I take this vertex and this vertex, what curve am I supposed to assign there? Okay, so you have to make a choice for how to model this. In the first papers we did on shape graphs, we put like kind of a constant curve there, which I didn't like too much. So we did a more complicated thing in the follow-up paper, where we do sort of a cone metric type construction, where we think of the edges as being weighted and valued in this shape space of curves, and then we identify any pair of points that have zero weight. And you can make this rigorous and make it work. So then in that case, your target Z would be sort of like a cone. All right, so then I'm really emphasizing essentially. So like I said, these original papers we did on shape graphs, we weren't thinking about the Z-Gromov-Wasserstein distance. In fact, they kind of inspired working on the Z-Gromov-Wasserstein distance as a way to formalize things. So everything that we did was like a bit ad hoc in terms of computing geodesics and things like this. But then in hindsight, like we kind of did it correctly, and they were theoretically founded in light of the Z-Gromov-Wasserstein distance. So in retrospect, it all works correctly. But at the time, it was a bit ad hoc. And then maybe let me mention that, of course, there are other ways you can model shape graphs. So there's a different approach in Sucre-Deep, Bauer, and Sharon, kind of using a more varifoldy type of formulation. Okay, great. So let's go back to the kind of general Z-Gromov-Wasserstein setting. So like I said, kind of the point of the paper is we can prove things in general about Z-Gromov-Wasserstein distances, which then automatically apply to all these variants, and you don't have to keep reproving the same theorem over and over again. Okay? So as a first theorem, the Z-Gromov-Wasserstein distance defines a metric on the space of Z networks considered up to a certain natural equivalence relation, which I'm not going to say exactly what it is, but as I said before, like we could say exactly what gets distance zero, and it's relatively a natural thing to describe. And it's basically like if I take a network and I kind of split apart nodes, but keep the kernel the same in a certain sense, it's like if I think of the kernel as a matrix, like a square matrix, if I make a copy of a row and a column, essentially what the equivalence relation is. Here's a schematic, but we're not going to really dwell on it too much. Okay, but then so let's let MZP denote the space of equivalence classes of Z networks with respect to this mystery equivalence relation, endowed with the P distance, the Z-Gromov-Wasserstein P distance. So then we prove some basic kind of point set topology properties of this space. So we show that it is separable, and so it's always separable, but we assume that Z is separable for this to make sense. And is complete if and only if Z is complete, okay? So we care about these properties because that makes this space also a polar space. So if you wanted to talk about measure theory on the space of Z networks, then it should be relatively well behaved because it has these properties. And then we show that it is contractible if P is less than infinity for any choice of target space Z. I want to talk a little bit about that last result because it's actually a bit subtle, okay? The proofs of the first two are relatively straightforward, I would say. The last, not as much. Because, okay, so if you compare to the Gromov-Hausdorff setting, if you wanted to prove that the space of compact metric spaces, or say the closure of that space with Gromov-Hausdorff distance is contractible, it's fairly straightforward. You take your compact metric space and just shrink all the distances to 0. You get a pseudo-metric space, which is isomorphic to the one-point metric space. So you can kind of contract everything to the one-point metric space in a straightforward way. Cool? That doesn't work in the Z-Gromov-Wasserstein setting because the ability to do that is based on your target being real line, which is contractible. Okay? If I take Z to be like a 2-point space, for example, then that trick is not going to work. Okay? But this theorem works when Z is a 2-point space, when Z is disconnected. But you can see the subtlety here. It doesn't work if P is infinity, which is more like the Gromov-Hausdorff setting. Okay? Because the trick to prove contractibility is kind of like messing with the measures and rescaling the measures instead of rescaling the distances, which doesn't work when P is infinity. And in fact, we show that if Z is not connected, the target space for your kernels, then MZ infinity is not path connected, so then of course not contractible. And thought about this for a while and couldn't get a full characterization, so this is an open question. How does the topology of this space depend on the topology of Z? Right, and then we think about geometric properties of the space of Z networks. We show that if Z, the target space for the kernels, is a geodesic space, then so is the space of Z networks, okay? And this is for any P, even P equals infinity. So once again, illustrating the subtlety of this previous problem. So if your target is geodesic, then you get path connected, for example. So what does this look like? All right, so when Z is R, right, then you're in the setting of classical Gromov-Wasserstein distance. It was shown that the Gromov-Wasserstein space is geodesic by Sturm. So the citation is from 23 because it was published then, but this goes back like 12 years or something where he showed this. Right, so it was shown to be a geodesic space. In a paper with Samir Chowdhury, we implemented the formula for geodesics, which if you read Sturm's paper, or our paper in fact, the formulation of geodesics looks kind of nasty, I would say. But in practice, if you're dealing with finite spaces, you can implement it fairly efficiently. And here's an example. So what does a geodesic look like? So remember, this is in Gromov-Wasserstein space. So space of networks. So I start with this network on the left. I want to end at this network on the right. I'm representing these in the Gromov-Wasserstein setting with adjacency kernels. Okay. And then the geodesic interpolates so through weighted adjacency matrices. It looks like this. So notice that there are different numbers of nodes, and the nodes are like splitting mass as we evolve through the geodesic. Yes. Yeah. So that would be an issue if the target space Z was like binary or something. Then I think then it's not path connected. So you don't. That's right. That's right. Yeah. So I'll show an example of that in 2 clicks. Yeah. No. That's great. Yeah. Go ahead. And then so this little tilde here is encoding this like mystery equivalence relation. But this one is not so mysterious, actually. This is just like a permutation. So permutations, of course, are included in this equivalence relation. This is like a bit more mysterious how these are related. So here I'm doing this expansion move where secretly there's like copies of these nodes sitting over each other. Right, so this is the idea. You're allowed to, or you can compute geodesics even between like graphs with different numbers of nodes. Here's another example. Here, this is in another paper where we're using heat kernels instead of adjacency matrices to represent graphs. This ends up giving you kind of nicer looking geodesics sometimes because it, it's kind of aware of cluster structure. Right, and then shape graphs, as was already predicted. So in this earlier work with Basu, Bal, Guo, and Shrivastava, we implemented geodesics in the space of shape graphs. And like I said before, we kind of did it in a slightly ad hoc way. It turns out that what we did agrees with the general formula that we proved. So everything lines up. All right, so here's this is a synthetic example. We just constructed these to have a nice picture, but then it works relatively well in real data. So these are actual retinal blood vessel networks and geodesics between them. And so maybe just to point out, like the geodesics here, so it has to kind of account for the difference in topology, different numbers of nodes and connectivity, but it also, the edge shapes are geodesics in the space of shapes. Account for both these. The same is true here. Here, yeah, as you mentioned, so we have to be able to phase out edges. So these are actually weighted edges, and we're really working in this kind of cone over the shape space. All right, so that suggests once you have geodesics that you could do other shape analysis-y type of stuff. Okay, so if you have geodesics, then you can think about doing things like exponential maps and log maps, which means that you can pull stuff back to tangent spaces. You can use that to do like iterative algorithms for computing means. So here's a bunch of retinal blood vessels. This is just showing the pipeline to extract them. But here's a bunch of samples. You can compute a mean using gradient descent with this kind of like geodesic version of gradient descent. Once you have a mean, you can log everything back to the tangent space of that mean and do things like PCA. So here is showing the principal components of this data set. You see that they're fairly interpretable, I would say. The first component is like bending motion in the middle of the, and they become less interpretable and a little bit more detailed as you go down the line. Great, and then so in this earlier paper, we also studied brain artery networks, which are more complicated and larger networks. And we did similar sort of PCA stuff. So we use PCA scores to featureize the data and do kind of classical statistics once you have these features. And you know, that worked fairly well. I'll end with some kind of future work. So in these earlier papers, really we were describing tangent spaces and tangent space PCA and all this really at a pretty intuitive level. So we're saying, we have these things we're calling geodesics. We can kind of synthetically say, okay, here's what a log map should look like. But none of that is really precisely mathematically formulated. So done at a more applications-oriented level, let's say. So future work, and we also haven't really precisely formulated the kind of Riemannian structure of the ZGW space ourselves either, so that is future work. And so how do you do this, right? So the Z-Gromov-Wasserstein space is an infinite dimensional space, and the question is whether it has manifold structure, and if so, can you access it computationally? So a couple of different approaches you might take. We showed that the Z-Gromov-Wasserstein space can be realized as a quotient of a Hilbert space. Okay, so if I take the space of maps from the square to my space Z, with Lebesgue measure, then there's an action by measure preserving maps on this space, and if I quotient by that action, then I recover the Z-Gromov-Wasserstein space. The issue, okay, so that feels like it almost gets you to the point where you can talk about manifold structure. An issue is like it's not a free action. It's the set of measure preserving maps is not actually a group. It's a monoid or semi-group. So the general theory that would tell you that quotients behave in some reasonable way kind of isn't there. So there's some technical work to do to make that go. Another approach would be to do it through curvature estimates. So let me refer to the Sturm paper. So in the classical Gromov-Wasserstein setting, where Z equals R, Sturm showed that the Gromov-Wasserstein space has non-negative Alexandrov curvature. So you can talk about curvature in a metric space by looking at comparison triangles, for example. And it's true that for spaces with lower Alexandrov curvature bounds, you can synthetically define things like tangent spaces and gradient descent and exponential maps, and it all works at a formal level. So then the question is, now suppose that I want to consider general Z, what are conditions on Z which would allow you to derive similar curvature bounds? Okay? So Mao has already done some work, and we believe that this probably works if Z is a Hilbert space by the same sort of proof. But then the question is, can you push this further? Okay, great. Yeah, so here are the references for the 3 main papers I was talking about. So thanks for listening.